Welcome to session 3 of the optimization lecture. Again, this will be a short one. Here we're going to talk about the Berndt, Hall, and Hausman algorithm for finding an optimum. And this is particularly geared towards maximum likelihood estimation. It is about estimating the likelihood function, so more precisely the log likelihood function. And the thing to note is that covariance between two variables actually gives information about how these two variables vary, and that's to say how they change in terms of x and y. Well, this is also true if we look at the covariance of functions other than variables, and in this case we look at covariances of the derivative of the function we are optimizing at a value beta. And this gives information regarding how the derivative itself is varying, which is to say here is the derivative, and we're looking at how that derivative changes with respect to changes in beta. But this should be recognizable. It's related to curvature. And this is what they recognize. They recognize that this is giving information about the curvature, and they noted that the p-lim of the quantity where you take the derivative of the likelihood function at the optimal value, essentially the sample average using 1 over n of the squared derivatives, is equal to the covariance of the derivatives at that point. Now, why is it the case? Well, I'll just point out these are the derivatives at the optimum. Being the derivatives, it would not be surprising to find out that the expected value of the derivatives at the optimum is 0, which indeed it is. And consequently, just the derivative squared gives you the covariance, rather than, as we would say, the derivative minus its mean, but the means are 0. So that's why you don't see the mean showing up here. It's 0. So they noted that, and they said, well, let's use the kind of sample analog of this associated with the particular point that we are at. Now, we're not at beta star, we're trying to get to beta star, but let's suppose we're close enough and we define this matrix beta related to, capital B rather, related to our current point. And they set up an algorithm that's very similar to our Newton-Raphson algorithm, in which we are currently at beta I. We have a certain step length, just like we do with the Newton-Raphson. But now instead of the inverse of the negative Hessian, we take the inverse of this B matrix, and we multiply by the gradient. The advantage to this is that B itself is always positive definite. So when you're trying to maximize the likelihood function, this will always put you in the correct direction. This will not send you in an opposite direction, which was a caveat or a problem with the Newton-Raphson in its purest form, at least. That won't happen here. And it's actually faster to calculate than the Hessian matrix that Newton-Raphson uses. But to note, the p-lim of this B matrix, that when it's not at the actual maximum, isn't equal to the covariance of the derivatives. And what that really means is that we're not actually getting accurate information as we get further and further away. So the further you are away from the actual point that optimizes the function, the worse the approximation will be. BHHH will tend to take a lot of steps. If you were to run an optimization from the same starting point using BHHH, it will take more steps typically than running a Newton-Raphson from that point, assuming the Newton-Raphson algorithm does not go in the wrong direction. But this is very helpful for many reasons, not the least of which is at least you're going to get there, so to speak, rather than heading off into a direction you don't want to go. So this is a very useful algorithm. Keep this in mind as you begin to pick your algorithms for doing your optimization, when you are going to be optimizing the maximum likelihood estimation function, you may very well find using the BHHH algorithm a suitable one for your purposes.